Hello everyone. This video is going to show you how to create or how to use a one-way ANOVA test or a single factor ANOVA test and what the output actually tells you, what the analysis tells you. So I'm going back to my crop data that I've collected, and when you use an ANOVA, you typically have some sort of a categorical variable that you're looking at. So we're going to look at, obviously, states. We've got Nebraska, North Dakota, and South Dakota. So what we're going to do is I'm going to look at the problem of, are grain yields in all three of these states the same? So what that means is we're going to look at corn specifically, and we're going to use our population because it's not the true population. So we're going to pretend that this is my sample, much like you have done for your final project. When you look at your ANOVA or your multiple regression that you do for your final project, I want you to use all 20 of your elements that you've collected. So what you're going to do is we're going to look at these 20 elements broken up into each of my state. So we're going to start by taking that and moving it here to a new page. And this is the same type of thing that you will do for your case study this week. You're going to use all of the data that you were given because they were samples. It's okay if they're not all the same. So you notice we have, I believe it's 6 from Nebraska, we have 9 from North Dakota, and we have 5 from South Dakota. So what we're going to do is we're going to run this single factor ANOVA test. What we're looking for is our null hypothesis and our alternative hypothesis. So right now, our null hypothesis, when you run an ANOVA, whoa, that got really small. We don't want it that small. So my null hypothesis, we'll put that right here. Whenever you run an ANOVA test, your null hypothesis is that all of the population means are equal. So what we're saying is that the corn yield from all three states on average is the same. So then your alternative hypothesis is simply that all population means. So we'll say are not equal. Those are the general forms of the null and alternative hypotheses when you're dealing with an ANOVA. So if we want to make this a little bit more authentic, let's rephrase this null hypothesis for our specific group that we have here, or data set. Let's get rid of these. So the null hypothesis would be that the population means of, so the corn yield from Nebraska, North Dakota, and South Dakota, or the mean corn yield, the mean corn yield from Nebraska, North Dakota, and South Dakota are equal. And then to get my alternative hypothesis would just be that same thing, except for we would say are not equal. So there are my null and alternative hypotheses for this specific, example. So we'll just do some wrap text. We'll merge those, cancel that. We want to merge and center that. We'll merge and center that so that we have a little bit nicer looking Excel file. All right. So those are my null and my alternative hypotheses. And this is what is always true when it comes to an ANOVA. The null hypothesis is always going to be that the means are equal. The alternative hypothesis is always going to be that the means are not equal. So to run the actual ANOVA, it's fairly simple. You go into that data package, that data analysis, so data analysis. Again, if you have a PC, this looks a little different. And then the very first one is ANOVA single factor. Click OK. And what you're going to do is you've got to find your input range. So for me, I'm going to start and go all the way down. Even if there are some blank cells here, that's okay. So we get A2 all the way down through C11. I'm going to make sure that I have labels in the first row checked because that's where my Nebraska, North Dakota, and South Dakota are. My alpha, we're doing that 95% confidence interval. And then for an output range, I'm going to say that we'll just do E1 so we can have this show up right in here. And then we click OK. So now we have this information from our ANOVA. So again, an ANOVA, what it's doing is kind of looking at the influence that one factor has on the data values. Okay? So what we find, we get our summary. So here's our count. Again, we have 6, 9, and 5. We have our sum of all of them. We have our average. We've got our variance. So that's what that first summary table is giving us. That's not a replacement for your descriptive statistics. Make sure you keep that as well. So then we look at our actual ANOVA down here. Well, what does all this stuff actually mean? So when we look at that SS, we are actually looking at the sum of squares. And this measures the variation between each sample mean and the grand overall mean, okay? We've also got the DF, that means your degrees of freedom. That's the number of values that are free to vary. So that's always going to be your number of variables minus 1. So we had North Dakota, Nebraska, and South Dakota, so we had 3 variables. And minus 1 means we have 2 degrees of freedom. We've got our MS. That means our mean sum of squares. So that's got this between and within. So when we look at between groups, we're looking at kind of the between and within providing a second and third estimate of the population variance if the null hypothesis is true. So it's giving us just another form of variance if that hypothesis is true. Next, we've got our F statistic. That's just that critical score. We've got our population value, or excuse me, our p-value. And again, we want this to be less than 0.05 in order to reject our null hypothesis. And then we've got this F critical value over here. So what we're seeing is if you look at this p-value right there, that is very, very small because that's got a e to the negative 6, which means we need to move our decimal 6 spaces to the left. So that's definitely below that 0.05. So this means we are going to reject our null hypothesis. So that null hypothesis was that the means from North Dakota, South Dakota, and Nebraska are equal. This p-value tells us that is not true. Okay, so what we're doing now is we're trying to figure out, okay, we know that they're not equal. Well, what does that mean? That means what are equal? Or which ones are not equal? Are none of them equal? Are only one of them not equal? So now we've got to do that Tukey-Kramer test to figure out, okay, so we know that not all of the means are equal, but since we've got 3 different categories, which ones aren't equal? All right, so now we're going to do that fun Tukey-Kramer, and unfortunately, Excel used to have a lovely button when you did an ANOVA that you just had to click it, and it gave you the Tukey-Kramer statistics and told you flat out, it gave you another table. They don't have that anymore, unfortunately, so we have to build it ourselves. All right, so what that means we're doing is we're going to look at Nebraska versus North Dakota and see how those means compare. We're going to look at North Dakota versus South Dakota and see how those means compare. And then finally, we're going to look at Nebraska and South Dakota to see how those means compare. So here are our pairings. Now we need to find differences. We need to look at our N for group 1. We need to find our N for group 2. And then we need to find our critical range. So what are we looking at, okay? And then we will have our outcome and our meaning. So here's everything we're looking at. Whoops. Let's go back. I don't know what I just did there. There we go. Meaning. Okay. So I'm just going to highlight all these because these are the top row of my table. So my Tukey-Kramer table. So make sure you do these tests to figure out if you come up with a difference exists in your means. You need to make sure you do the Tukey-Kramer test to make sure that you figure out which ones are different, if they all are different or not. So then we need to look at finding our critical F statistic. So one thing we can do is we can take we need to find it. So we look at our critical Q score. Q value, not score. And this is from page 852 in your text. Because what we're doing right now is we are trying to calculate the Tukey-Kramer critical range. And it's formula 11.11 on page 510. And if you look at that big, long formula, you'll see that we've got a Q with, or a Q there. So that Q comes from the appendix. So what we need to do is we're trying to figure out what that is. And in order to determine that, we need to find out what our D1 and D2 are equal to. To find that Q so that we can use that table. So D1 is simply just equal to the number of, variables you have, basically. So here we have 3, so our D1 is just equal to 3. And our D2 is a little more complicated because we're taking basically looking at our degrees of freedom. So we're looking at our within groups degrees of freedom. So D2 is actually equal to this within groups right here, that's 17. So you can either look there or you could do it manually and say, well, I have 20 different data points minus my 3 variables, and that's going to give me 17. Or we've got it in G16. So either way. So you could use that statistic right there as well to kind of give you that D2. So if you flip in your books to page 852, and if you go with your top variable, that D1 as 3, and the bottom variable as 17, we get 3.63. So that's what your critical Q value is. All right, now we've got to start filling in the table. So for our difference, what we are looking at is the absolute value of the difference in my average between my 2 variables. Okay? So what we're going to do is we're going to type in equals absolute value, ABS, And then we're going to look at the average of Nebraska and North Dakota. So there's the average of Nebraska, and there's the average of North Dakota. So we're going to do 1, 2. Oh, sorry, the difference between them. So absolute value of H8 minus H9, and we get 61. So now we're just going to drag that down, and we need to fix this one, obviously, because we want the absolute value between H8 and H10. So there are my absolute differences, and if you look, the first one, you can see that it's Nebraska and North Dakota. Second one is North Dakota and South Dakota. Third one is the difference between Nebraska and South Dakota. We do the absolute value so that it doesn't matter which one you put in first. If it's a positive or a negative, we just want that absolute value. So then we want the number in group 1. So this is my group 1 right here. So the number of Nebraska, so the count basically, so equals F8. And again, we can just drag that down. Now the next one, we want to start with North Dakota, so equals F9. And then for the, drag that down so you get F10 and then equals F8 again right there. So now we've got our counts. So now we've got to actually calculate that critical range. So in order to do that, we've got to actually type in this lovely formula from page 510. So we're going to start with our equals. And we want to start with that Q that we found earlier, which is that 3.63. So equals Q times, because we're multiplying this whole thing by that, the square root of, now we got to type in this whole thing. All right, our mean square within time divided by 2, or we're going to say 0.5 times the within groups right here, mean square root, so that H16, all times our 1 divided by our group for N1 plus 1 divided by our N for group 2. Close that up, add another parenthesis, and we get 20.95 blah, blah, blah. And then you just drag, well, when we go in here, let's absolute reference that Q value because we don't want that to change. And that H16 because we don't want that to change because that's always going to be our within groups mean. We do want the D22 and the E22 to change. So now we drag that down and we get 20, 22, and 24. So what that means, if you've read through the book, what you're doing now is we've got to make a decision and decide, okay, which ones of these are the same and which ones of these are different. So we look at now your difference and your critical range. If your difference is greater than the critical range, that tells you that the population means are different and you will reject the null hypothesis. So the outcome of this first one of North Dakota and Nebraska, 61 is greater than that critical range of 20. So we are going to reject. When we look at North Dakota and South Dakota, 19.7 is not greater than 22.1. So we are not going to reject. So we're going to fail to reject there. And then on our last one, Nebraska and South Dakota, we get 41 is greater than 24. So we again reject. So what does that actually mean? Well, it means here that our means are different. Or more specifically, the mean corn let's go back up and use our hypothesis. The mean corn yield is not equal between Nebraska and North Dakota. And we can just copy that same thing and paste it down here because we're doing the same thing. We're rejecting and saying that the mean corn yield is not equal between Nebraska and South Dakota. And when we fail to reject, that means our means are not different. Our means are equal. We'll say are not different. So the mean corn yield is equal between North Dakota and South Dakota, according to our sample and our evidence. So that's how you would run a one-factor ANOVA test and what it means when you're looking at it does give us a p-value that allows us to fail to reject our null hypothesis that all population means are equal, and then how you go about looking at are they all not equal, or is there some pairing where they may be equal. So from ours, we can see that Nebraska and North Dakota and Nebraska and South Dakota, when we compare those groups, we find that the means are different. But when we look at North Dakota versus South Dakota, we can't say that those means are different. And kind of thinking about it, it makes a little bit of sense that would be true because North Dakota and South Dakota are very similar.